Dot product has a definition. It's a way of multiplying our vectors together. So we've added vectors. Now we get to multiply them. The dot product of two vectors, u and v, if u is u sub 1, v sub 1 for the horizontal and vertical components, u sub 1, u sub 2, and v is v sub 1, v sub 2 for the horizontal and vertical components. The dot product, when we dot them together, when we multiply them together, we get u sub 1, v sub 1 plus u sub 2, v sub 2. So we don't get a vector back. We actually just get a scalar, a single number. So we multiply the horizontal components together, we multiply the vertical components together, and then we add them up. So if v is negative 2i plus 5j, and w is 4i plus j, how would we find the dot product of v and w? What do you think? Negative 2 times 4 plus 5 times 1. So negative 2 times 4 is negative 8. 5 plus 1. 5 times 1. 5. So negative 8 plus 5 is negative 3. That's the dot product of u and v, or v and w in this case. Easy enough? Okay. What if we wrote it in component form instead of linear combination form? If u is 2, 1 and v is negative 1, 0, what will the dot product be? Negative 2 plus 0, because 2 times a negative 1 is our negative 2, and 1 times our 0 is 0. So our dot product of u and v is negative 2. Easy math, right? I remember this being easy when I was in pre-calculus. Okay. Yep, I'll go back. I'm sorry. Now, just as we had some properties of vectors with adding and subtracting and so forth, and commutative and associative property following and so on, we're going to have some properties of dot products as well. You don't have to write these properties out. Okay? You can refer to them in your book. So these properties are on page 431 of your book, and they say, guess what? If we take a vector and dot it with another vector, okay, we can switch the order. Doesn't hurt anything. If we take 0 times dotted with a vector, we're going to get 0. The 0 vector dotted with 0 or with a vector is going to be 0. Okay, that 0 vector is basically a point on the origin, has no magnitude, no direction. We can take a vector and we can dot it with the sum of 2 other vectors, and it works like the distributive property. You would have the vector times the u plus the vector dotted with the v, or the w. And a vector dotted with itself ends up being its magnitude squared. Okay, that's kind of a unique one. If we dot a vector with itself, we end up with the magnitude squared. Okay. Why does that happen? Remember, if a vector has ordered pair, or has, not ordered pair, but has a horizontal distance of a and a vertical of b, and I dot that with itself, I'll take the first times the first and add it to the second times the second, And isn't that the magnitude squared? Okay. And lastly, if we take a scalar times the dot of the two vectors, it doesn't distribute through. It's only going to be multiplied once. It's like the scalar times the first vector dotted with the second vector, or the first vector dotted with the scalar times the second vector. Okay? So this is the one that doesn't work like you would think, not distributive property here. Okay? All right, so using the dot product to find the angle between two vectors. Okay, remember we found our magnitudes and we also found our angles, right? If we want to find the angle between two different vectors, we can use the dot product to do that. If theta is the angle between two non-zero vectors, u and v, then the cosine of theta will be equal to the two vectors dotted together over the magnitude of the first times the magnitude of the second. Of course, if we have those values and we do the inverse cosine, we'll find out what that angle is. So the cosine of the angle is the two vectors dotted together divided by the magnitude of the first times the magnitude of the second. Now there are technically an infinite number of angles between two vectors, because we can keep rotating around the unit circle, right? But this finds the shortest angle between those vectors. Okay? And it turns out that if the angle between the vectors is 0 degrees or 180 degrees, then those vectors have to be parallel. So what if we want to find the angle between u or v and w? When v is negative 2i plus 5j and w is 4i plus j. What's the first thing we have to do? I know you're writing, so I should pause, give you some wait time. Annie, put it away. All right, so the first step, we're saying that the cosine of the angle will be equal to, what's the first thing we have to do? Find the dot product, okay? So how do we find the dot product of v and w? Negative 2 times 4 plus the 5 times the w. The horizontal component times the horizontal plus the vertical times the vertical. So we'll get negative 8 plus 5, which was negative 3. Negative 3 is our dot product. It goes in the numerator. How do we find the magnitude of u? Yep, the square root of a squared plus b squared. So the magnitude of v will be the square root of negative 2 squared plus 5 squared. Oh, sorry. Yes, that's right. Negative 2 squared is, bless you, plus 5 squared. So square root of 29. Okay. And the magnitude of w? Will be 4 squared plus 1 squared. So 16 plus 1 is 17, square root of 17. Okay. Now we break out the good old calculator. And we say that we're taking -3 divided by, and if you don't want to make these into two separate radicals, you can call it -3 divided by the square root of 29 times 17. It's the same thing since they're both under the radical.
How did you get the -3 for u times v?
The u dot v means that we took the -2 times the 4, and then the 5 times the 1, and we added them up. That's where the dot product came from. Okay? So -3 divided by the square root of 29 times 17. And you get a -0.135, right? So if the cosine of theta is -0.135, we're not clearing our calculator here. Second cosine of answer in degree mode gives me 97.77 degrees. Okay. Did I do something wrong? Yeah. Okay. So don't do any rounding. Okay. Keep it in your calculator, then do a second cosine of second answer, and you won't have any rounding errors. And I got 97.77. Okay, because when you do a -3 divided by the square root of 29 and you don't close your parentheses, okay, then what's happening is it's then going to multiply that answer by 17. Okay, so you want to have your, you need to have, you can do it a couple different ways. If you want to take the square root of 29 times the square root of 17 and then do a 3 divided by that answer and then the inverse cosine of that answer, that's okay. Okay. Otherwise, if you do this, you have to put parentheses around the square root of 29 times the square root of 17. Okay, so you've got to be cautious with this one. Okay, either put them under the same radical or put a parentheses around them to make sure that all of the -3 is being divided by everything. Should be 97.76, I believe. Let me check my notes to see what I got the last time. I had 97.77.
Okay, so I multiplied this on the bottom and then, oh, I didn't.
So -3 divided by that, and then second cosine of the answer. Okay, everybody get 97.77? Okay, we're good? So calculator, you have to be careful. It understands order of operations, but it will not divide them by both of those two unless you either put them under the same radical or you put parentheses around it. Okay? Everybody good? All right. So, orthogonal. Orthogonal is our next subject header. And when you think of the word ortho, what do you think of? Teeth. And that's not really its root, is it? Teeth is more denty and so forth, right? Ortho, we think of because we think of orthodontist, and what does the orthodontist do? Straightens teeth, okay? And so it's making them match up, isn't it? Okay? So we're making not so much parallel, but they want them to be perpendicular to each other. They want them to form good angles. They want them to be right, okay? Orthogonal's roots, the word ortho has a meaning of right, and that's where this is coming from. So when we talk about orthogonal vectors, those are vectors that are perpendicular to each other. Okay? They form right angles with one another. So orthogonal means right angles. Well, the dot product is useful because it can help us decide in a really quick and easy format whether those diagonal or whether those vectors are forming right angles with each other, whether they're perpendicular or not. Because remember, the cosine of theta was the dot product, right, over the magnitudes of each of those vectors. Turns out if the dot product is, well, let's think about it. Let you think about it for a moment. If we want a 90-degree angle, what would that mean with regard to this formula? Cosine of 90 degrees is 0. Cosine of 0 it starts high, right? And cosine of 90 degrees is 0. Okay? So we want this to be equal to 0. How do we make that 0? Can we divide by 0? No. So do we want the magnitudes to be 0 when we multiply them together? No. We want the dot product to be 0. Okay? So if we make the dot product equal to 0, then the vectors are orthogonal. Okay? They form right angles with each other, perpendicular to each other. Okay. So we ask ourselves, are the vectors u and v orthogonal to each other? So we don't even have to figure out the whole angle. We just have to say yes or no answer here. If the dot product is 0, we say yes. The dot product is not, we say nope, sorry, but we don't have to even figure out what that angle is. So how do we find the dot product of negative 2, 3, and 6, 4? Negative 2 times 6 plus 3 times 4. That's our definition of dot product. Negative 12 plus 12. Yes. They form right angles with each other. If it's 0. Very good. Ready for the next slide? All right. A little bit of physics application here. In physics, we define work as the force times the distance. Yep. The force, the component in force in the direction of the motion, and the distance. How much force did we apply, and how far did it move? Okay. That is our work. Yep. And the key thing here is the component force in the direction of the motion. Okay, we realize that there's other forces acting, but when we want to know how much work is being done, we want to know how much movement did we make and what force did we use in that particular component. Okay. All right, so here we go. So we've got a tractor and it's pulling a log. Okay, pulling a log down the road. That tractor has pulled the log a total of 800 meters. Okay, that's our horizontal distance. Okay, and the tension in the cable attached to the tractor is about 1,600 kilograms of tension. and the direction of the force is 35 degrees above the horizontal. Okay, so this is a 35-degree angle. Okay, it looks bigger than that. I couldn't find a good picture of it. Okay, so we're going to ask ourselves, how do we find the work being done when pulling that log? Now we realize that there's some vertical work being done, right? It's lifting the log, okay? But we're only concerned about the component in the direction in which it's moving. So are we worried about the vertical component or the horizontal component? Horizontal, because we're moving it down the road. We want to know how much movement did we get, and how much lifting did the tractor do, but how much work was done moving that log. Make sense? Okay. So remind me, what is work equal to? Force times the distance. Okay. And we need to figure out what our force is. Okay. The distance is easy. We know that. It was 800 meters. Okay. So how do we find the force? $1,600 is our tension, right? And we're going to take that times, that's our magnitude, right? Okay. We're going to take that times eventually we're going to take it times 800. This is our 800. But first we've got to figure out our force. Okay. You're thinking of the 9.8 meters per second. You're thinking of the gravitational pull. What we're wanting to do, though, is we're wanting to take the force times, okay, remember, horizontal, what do we do when we want to define the horizontal magnet, or the horizontal component of a vector? Yep, the magnitude times the cosine of theta. That was our horizontal. Okay, the magnitude, we didn't give it a name here, we'll call it V, times the sine of theta was the vertical. Okay, so we're looking for only the horizontal movement. How much are we moving this guy? Because we don't know much about the lifting and what work was being done that way. We're going to take our magnitude, which is the 1600, times the cosine of what angle? 35 degrees. Okay, so that's going into the forces place. They're both supposed to be V's, sorry. Okay, and we're only concerned about this horizontal one. That's why we plugged 1600 cosine 35 in. Okay, and so 1600 times the cosine of 35 times the 800, which is going in here, is going to get us what? You do it all in one fell swoop. Make sure you close your parentheses on the cosine 35. And this was kilogram meters. We took kilograms times meters, so we end up with kilogram meters. Times the 800 eventually to get our distance in there as well. So if it was smaller than that, I did the whole final work formula. Not joules, right? You're used to physics being in joules, right? Uh-huh. Okay, or newtons, right? Okay. Okay. So this unit's actually kilogram meters, because we're taking a certain force of of kilograms, and we're multiplying it by meters. Okay. Are we good? All right. Assignment. Page 437. Mixture.